playing games with space and time. And at the end of the talk, we got up and asked the question, well, what's time? And I thought that was a very good question to put a whole topic into. And so that's what this is going to be all about. I've submitted this for the next AG, and we will find out, I hope within a week or two, whether or not I'll be giving it at the AG.
Okay, we're good.
You ready to go?
We are. Thank you.
So here is, that's the title. And I'll probably say I'm at Denver Mensa. And I'll start off by talking about the founders of the physics profession, if you will. There's Aristotle. Aristotle was a great at classifying things. He classified animals, he classified architecture, he classified philosophies. And among other things, he classified time in terms of human perception. In the past is what we remember, right now is what we sense, and in the future is what we can predict on the basis of what we got in the past. And I think with all of this, I'm going to give up on this laser because it's just too bright for the screen, and I'll stand and point. So, Aristotle held the field for 1,500 years to 2,000 years, and then Galileo came along. Aristotelian physics was all theory, really. The ancient Greeks on up through Plato were all about thinking it through, and mere evidence was beside the point. The notion of platonics and platonic solids was all about theory, and whether or not you could have a perfect circle, he didn't care. A perfect circle was where he started. So Galileo started with experiments, and everybody has heard about dropping the rocks off of the Tower of Pisa. He probably didn't do that, but he did a lot of experiments with rolling balls of various materials and various sizes down ramps, and ramps of different shapes, and trying to account for how fast the balls were going. And it turned out, as he discovered, it didn't matter what the ball was made out of, as long as they all had the same weight. Well, how did he do that when the time period between here and there is so short? And one of Galileo's really genius ideas was, I can weigh time. He would start a water clock going, dropping water into a bowl, and weigh how long, how many drops it took to get the ball from here to there. He had much longer ramps than my arms, but that was the idea. The idea that you can measure time exactly and then draw conclusions from relative amounts of times depending on the shape of the ramp and depending on what the balls were made of. So he was really started experimental physics. And the next founder of physics was, of course, Newton.
Yeah. Didn't he also compare the pendulum and the cathedral?
That's where he started. His very notion was comparing the pendulum's swing in church to his heartbeat, because it was a very boring sermon that he was listening to, and he was looking for something else to do. And then he started thinking seriously about time and getting on to this notion of being able to weigh portions of a second. I mean, his timing was so exact, and he was able to do it because he could weigh just a very small amount of water. So Newton's thinking in his time was all about, not all about, but he treated time as treated the universe as this enormous clock. All his mechanics are based on the notion that space and time are absolutes, and that he could do his equations looking at exactly how much time it took to get from here to there, and if you could do small increments of that timing, what conclusions could you draw? And then that held out from 1660s or thereabouts on to beginning of the 20th century, and then Einstein came along. And through a lot of Newton's more deepest notions into some disarray, as we'll find out. So here's our game plan, and I hate slides. I hate people to read slides to me, so I'm not going to read slides to you. I'll just let you read this for a second or two. That's what I plan to talk about. There will be some mild algebra, just to keep making it away. So we've heard about entropy being times arrow, that's what time is based on. And I've got a pink elephant here because there's lots of different ideas of what entropy is about. And once again, I'll let you read these if you want to. My point is that what you think entropy is depends upon where you came from. But the bottom line is that entropy increases in any real process, whether it's the randomness in a particular system or the size of the universe for cosmologists, or you see a lot of the science press, oh, entropy is randomness. It's a lot tighter defined than that. And it sets the direction of cause and effect. You can't have an effect prior to the cause, and I'll get around to that again a little bit later. So this is the weirdest definition of science, it's time. And the problem is that the Earth does not spin perfectly uniformly. It wobbles. If the poles start melting, that rearranges the amount of water in the northern hemisphere, where they are in Siberia versus where the water is in the southern hemisphere. Things get tilting. We think of the Earth, or the day, as being exactly 24 hours. Multiply it out, that's 86,400 seconds. Lots of physicists know that number by heart. And the problem is that those last digits are uncertain. And this chart to the right over there is talking about how that uncertainty has changed even within the last century. So back in 1960, they defined the second to be this. And there's some things there that bothered me. For instance, January 0, January 0 for the metrologists, the people who concern themselves with time, January 0 is actually December 31st. So that you can have day 1 on January 1. Tropical year, what's that? Tropical year is when the sun is exactly overhead on the equator. Okay. But they're talking about 1900. How do you get what the tropical year was back in 1900? That's where ephemeris time comes up. It's a theoretical time. Down at the bottom, you look at where the sun is at noon at the equator, year after year after year, and you build up records of where the sun is at the equator. And then over time, you build up a set of equations that describe this curve. Where is it on the average over time? So you can sync back year by year by using that equation, and then you have a sort of a theoretical time, and you can take that much of it to define your second. It's really arm's length and arm's length and arm's length with a stack of ifs, and that's bothersome. So a few years later, 1967, scientists said, well, let's just do away with Earth. we're not going to base our second on Earth's motion at all. Instead, we're going to take something that behaves exactly the same all the time, and that is individual atoms. Take a bunch of cesium, evaporate it, cesium atoms, and you look at what the cesium spectrum looks like very precisely. And furthermore, we're not going to look at the wavelength of the cesium. We're going to count exactly how many waves have occurred. It's a lot easier, it's a lot harder to figure out what a wavelength is when you're not sure when this is and when that is. So you've got a plus and minus that much. Instead, you set up your electronics to count when the wave goes up, when the wave goes up, when the wave goes up. And at that time, cesium atom in the millimeter wavelength range was cesium-133. You could actually count that number of periods. The electronics were fast enough so that you could watch what was going on. And that was pretty good. But it wasn't quite close enough. And here's where some audience participation is concerned. Put your hands up, make fists, stick your thumbs together. Okay, between one pinky and the other pinky is about 1 nanosecond for light to travel from one pinky to the other. You're holding a nanosecond of time in your hand, or at least for light to go. So with that, here's 1 second is 1,000 milliseconds, it's 1,000,000 microseconds, it's 1,000,000,000 nanoseconds, it's 1,000,000,000,000 picoseconds. And for one example, there is a remarkable experiment going on in Antarctica right now, and has been for a few years. Antarctic ice is very clear. And what they did was, I should mention this part, we're curious about neutrinos, and I won't go into what neutrinos are, but they're interesting. National Science Foundation and a few of the European countries all cooperated to sink almost 90 strings of detectors in a field a kilometer by a kilometer, sink it down, starting a kilometer down to another 1.5 kilometers. So you've got a cubic kilometer space of ice that you're monitoring very carefully. It's dark down there, but when a neutrino passes by, if you keep track of which sensors notice that the light flash from that neutrino, you can measure how fast it's going, you can measure what direction it's going, you can measure its energy. So if you can keep track of the picosecond time differences between flashes, or between detections from a single flash, you get a lot of information about that neutrino. So that's picosecond, a trillionth of a second. Everybody uses GPS. So we've got a spot here that happens to be Colorado, and you're looking at GPS satellites, and each of those satellites sends you a timing signal. And by looking at the difference between time signals that you get on your phone, you can triangulate or squarate or pentagonate. You can figure out where you are. And if you can keep your phone's time signals, if the phone can detect the differences within nanoseconds, you know where you are within a foot. That's that pinky to pinky. Okay? That's top down. But looking up, we have phased array telescopes. Anybody visit the large array, the very large array telescopes down in New Mexico? Tony, yeah. It's cool. You've got these huge radio telescopes on tracks that can run out as far as 23 miles apart. And if a pair of stars up here, if one of them gives off a jolt, and you can measure the difference in time between this telescope and this telescope, if you can measure the difference in time within picoseconds, then you can triangulate and see cool stuff. And in particular, if you are looking at an array of telescopes that is 8,000 miles wide, you can take the picture of a black hole. And those pictures that we've seen of the orange donuts that came out, that came from a distributed array keeping track of pulses, keeping track of the radio waves coming out of that first, the black hole at the center of Messier 31, and then the black hole at the center of our galaxy, and actually be able to make images out of the signals that they got. Very, very close timing, picosecond timing is required for that. You may have seen in the last few years some discussion of time crystals. These are amethysts, these are not time crystals. And what was that about? Well, you think that this cube, this array here is highly symmetrical, but there's symmetry it doesn't have. If that cube were water, and every molecule of water can move in any direction for just as far or as little as it wants, that's got a lot of translational symmetry that the cube on the other, cube with closely spaced atoms that everything stays in position doesn't have. So that is, we've broken the translational symmetry, and now we're down to a discrete symmetry where it's stepwise. It's the notion of breaking symmetry here. Well, we think of time as being continuous, but what if we could break time into steps that repeat? And that's what this I just rearranged these slides last night, sorry. So here's time as a dimension, here's an x and a y and a z. And consider the possibility that time is another dimension going from past to future at right angles to our x, y, and z. Okay? You're going to see this motif show up again and again and again. So in a time crystal, what they did, there have been a number of experiments, but the first one started with, they had some rubidium atoms. They just took some rubidium metal, vaporized it, and in that gas isolated a string of atoms, held them in position with lasers and with magnets so that they stayed in position. Then they ran another laser, very powerful laser, in this direction. Each individual atom can be up or down, or it can be oriented in one direction or another with a property called spin. I'm not going to get into what spin is, but we've got spins, and you can see here this particular set has some that are pointing toward you and slowly going up, and then slowly going around and forming an array. And they could measure that array with another laser coming in at right angles to it. And as a result, with enough power in this laser, they got these guys to line up, and they lined up not at the frequency of this laser, but at whatever frequency they felt like, so to speak. So that was a time crystal where we've got a structure in space, but it maintains, parts of the structure maintain phase with each other across time at right angles to the space dimension. It's a time crystal. And that gets us to the idea of instead of having translational symmetry in time, we can have a discrete symmetry in time. So let's live a little bit in 4 space. So right here we've got a 2-dimensional object, You can see one side of it, you can't see a back side of it because 2 dimensions doesn't have a back side. If we stretch that square out, we have a 3-dimensional object, and I've got it rotating here. This image took me about 10 years between when I first got the idea and then I did the further work until I could have a 4-dimensional object. You're looking at a tesseract. A square has four sides, each of which has 1 line. A cube has 6 sides, each of which is a square. A tesseract has 8 sides, each of which is a cube. And you are looking at a tesseract that is rotating, and you're seeing individual cubes come into and go out a position. And I'll take it one step further. A tesseract has 2 equators, and you are looking at something that's rotating in 2 dimensions perpendicular to each other. That's cool. You are looking at a 2-dimensional representation of a 3-dimensional slice through a 4-dimensional object in 5 space. Now you know why it took me 10 years to build this image.
Hey, Rich, I see you've got them lettered to come apart. Is there really just 26 signs?
I was using the letters to keep track of which faces were where.
Okay.
And that's faces of the squares, not faces of the cubes. So here's something else you probably have seen an image of. Klein bottle. The idea was if you take a piece of paper, roll it up in a tube, and then bring that tube around face to face, you get what shape? Torus or donut, yep. Now, the challenge is I've got my 2 fingers matching like this. What if I take that and try to have them match like this? So my thumb is against my thumb and my fingers are against my fingers. Well, you can do that. See, it comes around and it matches in, so it's thumbs against thumbs and fingers against fingers. But it had to break through this red area. We had to break through the skin. Is there a way of doing that without breaking through the skin? Well, yes, there is in 4 dimensions. It comes around, and the skin goes away when it comes time to patch up. So a Klein bottle, a Klein flask, and originally this was, Klein called it in German, a flash. And the people who translated it translated flash, which means surface. They translated it to flask. So this is Klein's bottle. It wasn't really supposed to be a bottle. But you're looking again at a 4-dimensional object. So here's space-time. And conventionally we've got time going vertically in a space-time diagram. And space goes perpendicular to that. So here's X, Y, and Z are all smashed into the disk around. And here's in the past is down, in the future is up. And here's Minkowski's hourglass. Conventionally, this is the speed of light. This is how far you can go in space in a certain amount of time. Okay? So our past is the bottom part of Minkowski's hourglass. Our future is the upper part of Minkowski's hourglass. What about this area? Well, say again?
We can't know.
Exactly. It's too far away to see. A Klingon spaceship could be out here. We have no way of knowing it until it gets to our future. What does that do for us? Well, it gives us a way of tracking from cause to effect. And that was the original question that the lady asked. And she said, what's time? At that point, it's the end of the hour, I said, cause and effect. Okay? So here's space-time, and here's one object. And it's not moving, so it's not going around in space, but it's ticking away at time on a regular basis. It's at rest. Okay? So here's two objects. Each of them is ticking away at the same rate, and they're both moving through space at the same time, so they've got, in space, they're both moving through space with the same velocity. We say they've got a shared frame. Each can keep track of what the other one's doing on a regular basis. Here we've got two objects, but this one is accelerating. It's changing, moving through space, and as it's moving through space, notice that its ticks don't match up with the other guy's ticks. This guy is moving in a different frame than this one, and the frames don't necessarily agree. And in fact, if you're moving fast enough, they disagree. And let's talk about this. This was Einstein's special relativity. And it's special, SP, speed, SP, that's one way of keeping track of special relativity versus general relativity. There is a factor here, the Lorentz factor, which we can use to measure how things change. Anybody recognize the orange car?
The Dukes of Hazzard.
Say again?
Dukes of Hazzard.
Dukes of Hazzard, that's the General Lee. And the Duke boys run around in the, yes, before your time, sorry about that. So the Duke boys run around and speed all over the county, Putnam County, wasn't it?
I think so.
Yeah. And they are going 67 million miles per hour, 10% of the speed of light. So if it's 10% of the speed of light, you can do the arithmetic, just plug in B over C, 10%, square that, take the square root of that, 1 over that, 1.005. What does that mean? That means, well, Bo Duke, one of the Duke brothers, in the General Lee, he's keeping track of the time on the General Lee's dashboard. He says it's going fine. The sheriff is standing there at his checkpoint behind the sign for the general store, and he clocks the General Lee, and he says that the clock is running slow by 5 milliseconds. Meanwhile, Bo Duke does the same measurement and says, Coltrane's clock is running slow. How does that work? Each of them is operating in a different frame. Remember those two spaceships going in different frames. Here's the equation. Notice that V is squared, so it doesn't matter if you're going this way or you're going this way relative to the other one. All that matters is the relative speed. So, kind of mystifying, but each of these two guys, both of them are right. The other guy's clock is slow because they're in different frames. And in special relativity, the other guy's clock is always slower than yours. You're always ahead of the time relative to everybody else. Okay? So there's two kinds of relativity. I sort of dropped that dime already. Special relativity, like I say, relative speed versus light speed. If your time is being dilated by 1 over this factor, your space is being compressed. And we've heard about compressed space near a black hole. That's what's going on here. General relativity is gravity near a concentrated mass. This one, our yardstick, is c. We compare the velocity with the speed of light. This one, our yardstick, turns out to be the radius of a black hole of mass m, but that's all right. All it is a yardstick. And you compare how deep you are in the gravity well to that yardstick. That's your unit. A couple of different ways you can write the correct equation, but the general idea is if you're deep in a well and someone else isn't as deep as you are, then your clock is running faster than his. If you're out here and somebody else is deep in the well, his clock is running slower. That's time compression against, or time dilation against space compression. Now do this. The other guy's clock may run slower than yours depending. And let's see how the numbers work out. Here's the Parker Solar Probe, which is the fastest thing humanity has ever set loose in the universe. This is a sensor mission that we sent out to take a good close look at the sun. We sent it out, circles closer and closer to the sun, had to pass by Venus a few times to speed up, and now it's going really close to the sun. It's going at 191 meters per second. That's 500,000 miles per hour at the time it got down to that many kilometers away from the sun. And it's zooming along. We've got two equations here. We've got the Lorentz time contraction from special relativity, and we've got this gravity dilation from general relativity. How do they compare? For time dilation, you've got to be really, really fast. There's kinds of speeds that we normally go to, the kinds of speeds that we can get with chemical rockets, they don't even show up. It's going to take a lot more than rocket propulsion to get close to light speed. So there's only 200 nanoseconds of time dilation from special relativity, doing the best we can with the Parker Solar Probe. But the gravity well that Parker Solar Probe has gotten into, his clock is running 1,000 times slower than special relativity clock is going. Is time starting to feel a little bit jello-y? We're seeing ways in which time can be adjusted, and depending how far down in the gravity well you are, your clock may be running slower than somebody else's. I just thought I'd put this up here. But it's relevant. We've got 1 minus v squared, and we're going to take the square root of that. And yeah, Lloyd and I had this discussion about imaginary numbers. Suppose the velocity is larger than c. Suppose this fraction is larger than 1. Suppose this number is negative. You've got a tachyon. You've got a particle that's going faster than the speed of light. Well, there's an implication for that in special relativity, because this factor will be some multiple of the square root of -1. It won't be a complex number. It won't be a plus b times I. It'll be only b times I. What does that mean? Here's our time dimension. This tachyon is going to be perpendicular to our time. What does that mean? It means that if the tachyon exists, we see it has gone. Maybe tachyons could have been produced in the intense chaos of the Big Bang. But they're in another direction. They're not in our universe anymore. Yeah, Victoria.
Just for clarity, my clarity, on tachyons, are these theoretical, or have these?
Purely theoretical.
Okay.
Never been detected. If one existed, and that's part of the point of this slide, if one existed, we wouldn't have time to
Yeah.
sense it.
And you can calculate its speed.
Yeah. But every once in a while, you'll see people talking about tachyons, and their world lines are perpendicular ours. We've got no way of measuring them, sensing them, even detecting them. So another thing that happens with people start thinking about time, suppose we could go back in time and kill our grandfather. Me being a grandfather, I'm not having that. It's popular with science fantasy writers, but you can't. And let's, if you notice, we've got some planes moving along the time axis. Suppose we had a time loop. All of a sudden, some object is following this time loop, bang. As far as the universe is concerned, that's energy that wasn't there before. That's mass that wasn't there before. And that breaks the law of conservation of energy. Go another step along the line, and another step, all of a sudden that mass disappears. It's pop, it appears, going around the time loop, pop, it disappears. And in the middle, you got three of them. So it's not just one failure of the conservation of energy, it's three failures of energy, and on one of them is going backwards. It's kind of hard to make anything real out of that unless time is multidimensional. Remember that tachyon going perpendicular to our time? Maybe if this is a spiral, you could do that. So let's look at a single world line, and maybe you could have alternate histories. That's this one going here, where it goes in a different past and a different future than ours, or a parallel time track and alternate history. That demands you've got to have at least planar time and possibly higher dimensions than that. More dimensions in time than we can cope with. Like I say, Einstein's equations are already too complicated to solve, and here they're really complicated. When you've got multiple versions of time, when you have to start thinking about in space-time, there's, and this is one of the Newton's notions that we break, we don't have an absolute. That's the only point in everything. You have to measure things relative to other things. You have to see what's the interval between these two. You have to see, all of a sudden the notebook comes out, cool. So here's a situation where Lloyd is on Earth, and one of our other Mensons is over here on some other planet a long way away. And there are two novas that go off. And or Lloyd rather, is on Earth, and he sees those two going off at the same time. And this other astronomer on planet XYZ sees those two novas going off. But they don't seem to be going off at the same time. The astronomers have this notion of proper time, or cosmologists. If the clock is running along a timeline, that's its proper time. And because of relativity, other objects can have other timelines. We can look at the difference between time 1 and time 2 as seen by B, and the difference between those two times is seen by A, and the same factor, that 1 over velocity divided by c squared, applies to convert from this time difference to that time difference. We good on that? You're looking at a delta in time and a delta in time seen according, one's going at a different speed than the other. The only time you can have simultaneity, the only time that these two time measurements would agree is if that is zero. If that's zero, then this is one, and those two agree. The only way you can have two simultaneous events, or two events appear to be simultaneous, is if these two guys are traveling exactly in the same frame. If one is accelerating relative to the other, or they're going at different velocities, greatly different velocities, they're not simultaneously. And Einstein pointed out that simultaneity is an illusion. It looks like two things are simultaneous to you, they probably aren't simultaneous to anybody else. So there's the notion of time. Which frame are you in? If you're a slowpoke and there's a photon going past you, and anything short of light speed, you're in a slowpoke. You're looking at this velocity, you will see the difference between those two. Apparently, photons have an infinite proper lifetime. Excuse me. If you are a photon and you are traveling along and measuring your own proper time, if you've got a clock that travels with you, the difference between when you started and when you ended is zero. From the photon's point of view, when it was created and when it ended, zero time. It stops as soon as it started. We're going to have to re-raise this. But if you are anything else, then it looks like the photon has an infinite life. And there's a fun fact for you. The photons that were created back in the Big Bang, 99.9+% of them are still going. Infinite lifetime, because they haven't hit anything yet. There's been a lot of discussion about particles and waves, and when is it a particle and when it's a wave. And the best way I found to think of it myself is, when it's traveling, it's a wave. When it stops, it's a particle. So this photon is waving along until it stops. Black holes have been an incredible laboratory for us for thinking about time. So let's talk about black holes a little bit. Here's one way to build a black hole. We've got a star here, and it's burning hydrogen across time, and it's burning more and more hydrogen. And finally, it runs out of burnable hydrogen, and that's carefully phrased. It can't get to all the hydrogen for various reasons. And so you get an explosion, and you get a black hole. And that's typically 1.5 to 5 times the mass of the star. It will collapse to either a black hole or a neutron star. You can have black holes that are larger than that. That was a big surprise. The very first black hole collapse that we ever saw, back in November 2015, was when two black holes collided with each other, and the LIGO instruments in Hanford, Washington, and Livingston, Louisiana, both saw the same collision in a gravity wave. That was two black holes that were roughly 30 solar masses each. And that was one of the things that blew a lot of people's minds. We didn't know how to make a black hole that was that big. There's bunches of them, and this is a few years ago. Bunches of them that are in the 30 to 60 to even 100 solar mass size range. That's not solar collapse, that's some other process that's made those black holes. We don't know what it was. And then we can get to huge black holes, the supermassive black holes that are at the center of galaxies. We have no idea how they're made. There's a number of hypotheses, a number of ideas. Maybe gas just squeezes in and makes a black hole directly without going through the process of star formation. Or maybe a galaxy cluster gets together, we don't know. Anyhow, there are a variety of black holes, but all of them are mysteries or provide us opportunities for throwing out different theories for how they could operate on space-time. Anybody's here seen the Interstellar movie? I've seen a lot of, yeah. This is Kip Thorne. He was the science advisor for that movie. And he is a big name in black holes. He was one of the three, the triumvirate that drove the project to make the LIGO Observatory. So when, his name escapes it, when the producer of this movie, Nolan? Christopher Nolan? Yeah. When Christopher Nolan was working up the ideas for his movie, he got in touch with Kip Thorne, who was at Caltech at the time, and said, we need to work out what this black hole is going to be. The black hole is going to be one of the major plot elements of the movie. He wanted his spaceship, I'm going to leave out all the plot in the movie, their spaceship has to be in a parking orbit around this gigantic black hole named Gargantua, down here. And from the parking orbit, there's going to be a shuttle that comes down to Miller's planet. That was the water planet that people drowned on. And there has to be a difference in time, in the way time works, between the parking orbit and Miller's planet. And Chris Nolan said you need a factor of 30,000. So the 23 hours down here is 7 years up here. The plot demanded it. It had to be that way. So Kip Thorne proceeds to turn the mathematical cranks and figure out how big and how large and how fast Gargantua has to be in order to make all that happen. And Thorne, while he was working on it, see this picture of the black hole. Before Kip Thorne had done this work, we thought of black holes as being this black sphere in space. And if we were generous, we would think about there being an accretion disk running around the black hole in space. Just be this disk of stuff. Stuff comes in from some other funny angle, goes further down, and then comes back, and you wind up with this disk shape. Things seem to like disk shapes. The solar system is a disk shape. Milky Way is a disk shape. So we all expected that there would be an accretion disk about the black hole. This hoop, up and down, that's light from behind the black hole, from the accretion disk behind the black hole, being bent around, and we're seeing the section of the accretion disk that's behind the black hole, we're seeing it above or below. That's the light that's being bent, diverted, going past the black hole. So that's behind the black hole, that's above the black hole, as this thing is rotating at this enormous rate of speed. We didn't realize that until Kip Thorne had to do the graphics for the movie Interstellar. So this was a case where science and art and science went back and forth. So here's dead space-time, there's regular space-time, and here's where there's a black hole, and we are pulling in space around us. Okay? So if light were going through here, it would get bent, and And here's a spacecraft going past, and it's going in a straight line, and it thinks it's still going in a straight line, but the space it's traveling through is bent. And so from the outside, we see it moving in a way that we didn't expect, except for the gravity of the black hole. Gargantua is rotating at a great rate, as fast as it can. And that was one of the constraints that Kip Thorne had when he was doing his calculations. The outside edge of the mass that makes up Gargantua is going at light speed, or just shy of light speed. Any faster, matter would be flung out of the black hole. So this was a maximal black hole. And what does that do? He needed what's called a soft edge. You can get close to a black hole without going in, and it doesn't harm you, as long as you don't go through the event horizon. He needed a soft edge, and he needed this 30,000 times time dilation. When you're going around a black hole that fast, or excuse me, when the black hole is rotating that fast, there is a region here that space is dragged around. And it's hard to visualize what that looks like. But you're going through and you are getting into this ergosphere, and you're going around that black hole almost as fast as the speed of light. You don't feel like you're traveling at all, but the rest of the universe is going bonkers around you. And if you are looking at the right angle, you see some of these guys going around apparently faster than the speed of light. Oh, breaking the law. No, you're not breaking the speed, you're not breaking the law. Space is traveling as fast as it feels like, and you're just going along space. Like I say, Albert Einstein laughing. While you're in this ergosphere, you could indeed go back in time. It's a little risky, but it's possible. If the thing makes spirals, and if the speed is fast enough and you get into one of those spirals, you can quantum tunnel between levels of the spiral. And that gets strange. Like I say, the equations get funny. So let's talk about the event horizon a little bit. This is that same formula that you saw already. That just gives the diameter, twice this gives the diameter of a black hole's event horizon. And here's that same formula that you've seen before. You recognize cause and effect going this way outside the black hole. Einstein's equations, once you get past the event horizon, Einstein's equations say inward is the only way to go. Gravity is so intense you have no way of moving out. Cause and effect are so intense you have no way of causing anything outside of yourself. Further out. Cause and effect is in. If I were in here and shoot off skyrockets, all the skyrockets go that way. You can't make any sparks go out that way. It's not because photons can't get up to escape speed. Photons have zero mass, and the whole equation that works up to escape speed doesn't count, because zero mass. But the sparks that come out of the skyrocket don't go out, they all go in. So if cause and effect goes out up here, and cause and effect goes in down there, at some point, cause and effect is right on the edge. That's what a black hole event horizon is. So anything that you shine a spotlight down here, just outside the black hole, it goes out. Just inside the black hole, it has no choice but to go in. Okay, that's enough of the black holes. Quantum mechanics. Like I say, if it's moving, it's a wave. When it hits a particle. I love this graphic. So this object here is giving off a photon. And that photon is just a packet of energy, and it really does spiral when you look at the equations. And if you look close, just at the time that that spiral was created, there's part of it that is back up earlier in the time stream. Here's its timeline. It gives off a wave right here, but in here, earlier than 0, there's a wave. It's just the way the math works. And that is what gives rise to Heisenberg's uncertainty principle. So let's look at that for a little bit. The uncertainty principle, you've seen it about, well, I know where I am, but I don't know what my momentum is. There's a limit to how close that you can measure those two. I know what angle I'm pointing at, but I don't know what my angular momentum is. Those two quantities are linked together. There's also, in the equations, there's a link between energy and time. I know how much energy, wait a minute, I said there's no absolutes. So I can talk about the difference in energy, and I can talk about the difference in time. In earthquake prediction, we know the little ones happen fairly often, the big ones happen less often. On the average, the little ones happen every so many days. On the average, the big ones happen every so many days. But you don't know when the big one is going to happen. It's similar to, but not quite the same, as looking at the lifetime of the state. We know when this particle raised its energy level, and we kind of sort of know when it collapsed again. The lifetime is steady state. But we do know that there's an uncertainty there. There's room for variation. And by the way, that's a very, very small number. 10 to the minus 15th electron volts per second per particle. So it's a really small, but it's enough to make spectra happen. We wouldn't see rainbow if that were 0. We also wouldn't see rainbows if that were anything much bigger than that. So I've talked about when it starts, when it ends. How old is the universe? Let's go into the evidence on that. Over here we've got a pair of yellow lines. That's sodium. If you heat up sodium vapor, it gives off the yellow color. You go outside at night, if you've got sodium vapor lamps in the neighborhood, you get that golden color. If you shoot off fireworks that have a lot of sodium in the load, you get that golden color in fireworks. That's a very easily recognizable doublet, pair of lines, doublet. And in the spectrum, in the solar spectrum, that's a pair of dark lines right there. Why are they dark? There's sodium in the sun's atmosphere. Underneath the photosphere, underneath that atmosphere, you have a continuous spectrum because you've got a whole lot of heat. Every possible frequency is being given off. The sodium in the sun's atmosphere absorbs those two particular colors, that doublet. So there's a dark line, a Fraunhofer line for sodium in the sun's atmosphere, in the sun's spectrum. So we look and see what, for some other object out here, what does its spectrum look like? And its sodium lines are shifted. Red shift and blue shift. The sodium lines appear in the spectrum at a little bit different point. And Hubble worked out a lot of work so that we know from 1 billion years ago, we know how much shift a particular object has experienced. A star out there is a redshift of 0.7. A star out there is a redshift of whatever it is. and we can see how fast it's traveling from that redshift. The further away it's going, the further the redshift is, and we can measure its distance by that redshift. 20 kilometers per second for every million light years away it is from us. Well, you track that back, there's where the farthest star is, out of not quite 13, redshift of 13 billion years ago. So the earliest photons we can see are 13.8 billion light years. But wait a minute. People say that the universe is 47 billion light years in radius, the observable universe. There's a difference between photons that were given off at the Big Bang and we're still picking them up. Remember, the Big Bang photons are still coming here from 13.8 billion years ago. But fresh photons are being built and given off 47 billion light years away from us. We just aren't going to see them for another 47 billion years until those photons get to us. So it's the difference between fresh photons and early ones. So that's how old the universe is. What about before time zero? There's two possibilities. Stephen Hawking said, if you're traveling south on the Earth and you get to the South Pole, you want to go further south? You can't. There just isn't any further south. Everything from the South Pole is further north. That if you read his A Brief History of Time, he's got this diagram, or almost this diagram. There's another possibility. Remember we said, and this is basic to physics, all physics is object relative to object. If the universe is all by itself, if there's nothing else, and it's just sitting here, there's no way to measure distance away from it. Because there's nothing to be relative to. There's no way to measure time before or after it because there's nothing for it to be relative to. So one possibility is there's no time outside where the universe is. There are a number of models of how time works. Einstein, in several of his writings, mostly philosophical writings, he was fairly clear. His feeling is that space-time, all of space-time, was like jello, fixed. That we are consciousness traveling along fixed timelines. He wrote a note of commiseration to someone who, one of his friends who had passed away. And he said his consciousness has stopped, but his timeline continues. Or words to that effect. He thought we had a closed block, that everything is fixed. There's a single quantum state, and there's a clock that just ticks along as we recognize various parts of time. And that's compatible with relativity. There's another possibility that only the past is fixed and we're continually building new time as we go along. The time in the future doesn't exist yet. There's a problem with that, and I'll get to that in a second. This is the other reason for doing this pitch. We could talk about emergent time. Under vigorous discussion. This is, anybody recognize this asterism?
Is that the Pleiades?
Bingo, yeah, that's the Pleiades. And if we look at the gravity field of the Pleiades, each of these is a pit, around each star. And within that pit, there's time dilation. Gravitational time dilation, general relativity, just as we've seen before. And what that means is, as we are experiencing time, or as a spaceship, for instance, is experiencing time, this one doesn't, the one coming up underneath this pit doesn't experience as much time dilation as this one does. Excuse me, experiences more time dilation as this one does. So in this area, it's a private time. And if you think back to this, more. If you think back to this image with time slowly filling up the 10 time base, there's pits here, where different parts of the universe at different times. Relativity theory can't cope with that. It makes it difficult. So what about infinite time? As the universe continues to expand, as entropy continues to level out the universe, maybe we have a chill. Maybe we just, all the energy in the universe is infinitely, is perfectly spread out, and nothing can happen evermore forever and ever. Maybe that's one way the universe ends. The clock stops ticking because nothing can happen. Another possibility is it gets so big and then for some reason it gets small again. That's the cyclic universe. That was the leading theory back when Einstein was starting to think about this kind of stuff at the beginning of the 20th century. Another possibility is a big rip. There is quantum mechanical reasons for thinking that possibly a flaw in the structure of space-time can start moving out as fast as it can, which is at the speed of light. And it is just, behind that flaw, there's nothing. Ahead of that flaw, there's no prior notice, because we can't tell it's coming until it gets here. It's possible. I don't like it. If you look up Katie Mack's book, she's got a whole list of other possible ends of the universe. And with that, thanks for your time.
Rich, when are you gonna start?
Huh?
When are you gonna start?
I did want to make mention, I'm trying to shut off the there.
Still on, maybe it's in the future. Still on.
There's a cap that's in my pocket. There it is. I figured out why they sent me this little metal cap when I bought the laser, because it splits the picture all cool, and that way I don't have to worry about the laser getting in someone's eye.
Please give me a bunch of party. What do you got?
It's supposed to, there. Now, if I can get this to, they also sent this little plastic cap to put over. There.
Just on,
Yeah, Victoria, you had a question?
Now, this is confusing and fascinating, and now it's got me wondering, what exactly is space-time? I always, because how can space-time, is it just because it has matter in it that it can be warped? Or is space-time a concept? Or is it just really the area in which large things with mass roam around?
All of the above.
I see.
Let me ask it this way. What's the orbit of the Earth?
The orbit of the Earth is the ellipse of which it travels around the sun.
So it's a mathematical abstraction of all the points
Right,
the Earth has
the orbit
followed.
is, but it is, but the orbit, but it is but it is, that is a non-physical thing. It's a concept that is describing a physical thing. Okay, that we can observe. But when you get to the part of space-time being warped, which I've heard is caused by gravity, which is caused by a bunch of real stuff. And it is but what exactly is it warping?
I'm gonna go beyond what I'm certified to talk about. Okay. We're saying gravity is a way of saying there's a lot of mass here. But dig down a little bit further. Mass is all those atoms, and each of those atoms is a twist of space-time. Now spread that out. What you're looking at is a distortion of space-time. In large quantity, you have cooperative distortions of space-time. That's where the notion of emergent space and emergent time comes from.
But what about a piece of space that is not, has no matter in it at all? Nothing at all in that particular space. Would it also be warped by the effect of that large mass a couple million miles away?
It'll be, the gravity field is infinite.
Yes.
And when we talk about I hate this image, but there it is. When we talk about a depression in the gravity field, when we talk about gravity wells, what we're talking about is increase in the strength of the field. Okay? And where does the gravity field comes from? It comes from the energy that's wrapped up in the atoms and the nuclei and the quarks and the binding energy.
But again,
The interaction between space, time, and energy is what we're talking about, and we don't know enough about it yet to talk about it.
I can buy that. The other thing is it just blows the theory of, when you first started, you talked about time as fourth dimension, and that would make it is, if it is a dimension, it is not at all. Let me back up and say, we are in three dimensions, physical dimensions. We can move forward and back at our will. We can go up and down at our will. Yet, a fourth dimension that only allows us to go one way. Why?
Yes. That was that
Yeah,
models of time,
right.
the time base. And is it just our consciousness that moves forward in a fixed space-time, or is it we are at the very leading edge, if you will, of time building itself?
Oh,
I like that idea myself. I don't like having a fixed future. I like to have some free will. And time building itself as we move forward.
well, you'd still have time will, you just, you could make all the will you want, you just don't know that it is, your ultimate decision is observable in the future, or in the past.
If my plans work
It's
out.
the tachyons, Rich, it's the tachyons.
Yeah, Cody?
No.
So this is more or less what I propose to talk about at the AG. How long did it take? An hour and 15 minutes. I'm gonna have to pull some stuff out.
No, it took an hour and 14 minutes and 15 seconds.
Back there over there.
Yeah.
Approach a black hole and give it faster.
There you go.
Yeah, do that the equator, not normal.
It's supposed to be 45 minutes plus questions, and I'm not sure whether or not I can do all that.
Do you have to answer the questions, or can you go?
The answer's always gonna be yes.
Great,
Yeah.
okay, bye.
Yeah, good, Dad, so do I.
I mean, good, you know?
Well, thank you very much.
Good job.
Thank you for hanging around while I try this out.